Welcome to Unit 7. In this unit, we're going to be looking at Section 7.1 entitled Definition of Sound. Now, before we look at sound in detail, and before we define what sound is, it's very important that we have a look at the learning objectives for this particular section of the unit. So the learning objectives are as follows. Students will be able to define what sound is. You'll also be able to understand how sound reaches our ears. So let's have a look at a definition of sound. So when we talk about sound, what exactly do we mean by the term sound? It's a term which we understand quite readily in terms of our interactions every single day of our lives, but from a physics point of view, what is sound? Well, sound is a form of energy that is generated by a series of vibrations of an object. So in other words, sound is generated in the form of energy when an object vibrates. So let's have a look at this in a bit more detail in terms of what this specifically means. Let's say we have a tuning fork, and some of you may have come across this in the science laboratory. A tuning fork is a device which looks a little bit like this, and if you were to take a tuning fork and you were to strike it against a block of wood, then what you actually observe is that the tuning fork vibrates and you actually hear a sound. So when you take this tuning fork and you gently strike it against a block of wood, you actually hear a sound due to the vibration generated by the tuning fork. Sounds are made when an object vibrates. Now here we have a series of different types of situations where vibration is taking place. So what vibrates in each of these images in order for them to make a sound? So if we look at each one of these in turn, what you can see is that we're here in terms of this lady now who's singing, holding the microphone. It's her voice box which vibrates, and the vibration of the voice box generates the sound as she sings. In terms of these speakers, the reason why these speakers are able to make sound is due to the vibration of the loudspeaker cones inside of these speakers. And the reason why this drum is able to make its traditional sound is because of the vibration of the drum skin. And finally, the violin is able to produce wonderful sound due to the vibration of the violin strings. So in each one of these examples, you can see something actually vibrates in order to produce a specific sound. Now, there is a fascinating experiment which is usually done in laboratories to prove that in order for sound to actually be produced, it needs a medium. And to explain what that means, let's have a look at the diagram. If you were to place a ringing clock inside of this bell jar, what do you think would happen? Well, what would happen is that by placing the clock inside the bell jar, because there's air inside of the bell jar, you will hear a sound. The sound will travel through the air inside of the bell jar, and you will be able to hear the sound of the bell ringing inside that bell jar. Now, what would happen, do you think, if we were to remove all the air inside of this bell jar? So in other words, if we get a vacuum pump and we pump out all of the air from that bell jar, and remember the clock is still ringing, then what will happen is that as you gradually remove all the air using the vacuum pump, then the sound will get gradually lower and lower and lower, and there'll come a point where the sound cannot be heard. There is no air inside the bell jar. In other words, you have created a vacuum inside of that bell jar. So the fact that you're unable to hear the ringing of the clock, despite the fact that it is ringing when you remove the air from the bell jar, shows that sound needs a medium in order for it to propagate, in order for it to move, in order for it to transmit. So without any air, you cannot have the transmission of sound. And that applies to any form of medium. For example, you can hear sound in water. You can hear sound as it moves through solids, just in the same way you can hear sound as it moves through air. So it's very important that there is a medium, and this experiment in many ways proved this to be the case. In other words, remove the air from the air jar and you will not be able to hear the bell ringing inside of the bell jar. So hopefully what you should have noticed from the animation is that as the pipes are tapped, in other words, as the individual who is 7,000 feet away along the tunnel, as that individual hits the pipes, then what you should have seen from the animation and what you should have heard is that the sound travels along the pipe very quickly compared to the sound that travels through the air. So in other words, you will hear the sound through the pipe first, and then after a delay of a couple of seconds, you will hear the sound of the individual yelling 7,000 feet away from you in the tunnel. So in other words, this proves that sound actually travels a lot quicker through metal, or in this case through the pipes, than it does through air. So in other words, the individual in the tunnel who hits the pipe is sending a sound wave through those pipes which are traveling extremely fast compared to the sound waves which are traveling through the air. And this in a way is a very good demonstration in terms of showing that sound waves travel a lot faster through solid media, in other words the pipes, than they do through air, which is a gas. So this now brings us to the question of how does sound waves travel through a medium? And again, this is really sort of just going over what we've already looked at in Unit 7.1. But just to summarize, what we can say is that sound travels at a slower rate in air, but travels much faster through a solid. And we've looked at the reasons why, and this is because as sound travels through a solid, it does so because of the collision between the neighboring particles as they vibrate in the solid medium. So in the case of a solid medium, the particles are closely packed against one another, which means that the vibration can be transmitted quite easily from one particle to another because they're touching each other. A bit like, for example, the domino effects. When you have a domino and you drop a domino and it hits another domino, and then it continues the pattern of colliding or hitting the neighboring domino. Whereas in a gas, for example, the particles are not arranged in this manner. They're actually arranged so that they're further apart from one another. So as a result of that, the vibrations, for example, of an air particle will not be readily transmitted to another air particle in the same way that it would be in, say, a solid. Now, this probably leads us to a very interesting question, and the question is, why does a closed door block out noise? And the reason why you may ask that question is because if solids are very good at transmitting sound and transmitting it faster, then why is it that if we stand at the other end of a door or a wall, why is it that the sound seems to diminish? In other words, why does a closed door, or a wall for that matter, why does it block out noise? Well, as I've just said, it's true that sound waves do travel very quickly through solids. But on the other hand, we know that solid objects, they do block out sound waves. And the reason for this is actually quite simple. Now, when the sound originates from a particular source, as in this diagram, you can see that these waves represent the sound energy originating from this individual here on the left, then what will happen is that those sound waves will travel through the medium. In other words, through the gases. It will allow the sound waves to travel through the gas particles via vibration. Now, when those sound waves which are traveling through the air, in other words, traveling by vibrating the air particles, then when it reaches the solid object of the wall, it actually loses some of its energy. Now we can visualize this by this diagram and animation. And what you can see is that there's an incoming sound wave, and what we've got here is that the sort of red waves represent the incoming sound. And then you can see that when it hits this hard surface, that there is a reflection of the sound waves. And so what happens is that some of the sound waves will be reflected from that wall. At the same time, some of the sound waves will also be absorbed by the wall, and it will depend on the materials that the wall is made up of. And then also some of the sound waves which are reflected and absorbed, that will indicate that the remaining waves which actually go through the wall, that's going to be diminished, because if we have sound waves which are reflected, sound waves which are absorbed from the incoming sound, then that means the remainder that goes through is going to be a smaller amount. So in other words, a change in the medium, which is from air to solid, triggers a reduction in the energy being carried by the sound wave. And that's why we say sound lose their loudness when they run into different medias. And the reason why they lose their loudness is because of the energy is being diminished. And remember what we said was that energy of a wave is associated with its amplitude, with the height of the wave. That means the height of the wave coming out through this wall is going to be a lot less than the height of the wave which goes in terms of the amplitude of the wave. And so that would explain why a closed door blocks out noise. So let's have a look at a few checkpoint questions to round up this particular section of the unit. So we have a series of 5 checkpoint questions, and I'm just going to go through them with you. And then I'm going to ask you to pause the video and then try and answer these checkpoint questions. And then when you're ready to compare your answers with the answers that I'm going to provide, then you can press the play button on the video. So let's first of all just go through the checkpoint questions for 7.2. So the first one is describe how sound is produced. That's the first checkpoint question. And then the second checkpoint question is describe the importance of the material in the medium for the propagation of sound. In other words, why is the type of material important in terms of whether or not sound is propagated through that medium? And then the third question is, what are the 3 requirements of sound? And then the fourth question is, what does vibration mean? And then the fifth question is, write some sources of sound. In other words, how is sound produced in terms of various different types of sources? So have a go at these checkpoint questions, and then when you're ready, then you can press the play button, and then we can go through the solution to these questions. So now press the pause button and have a go at these questions. Okay, let's have a look at the answer to these checkpoint questions. So in terms of the first question, what we can say in terms of an answer is that all the sound that you hear and that I hear, that all of us hear, is produced by a vibrating object. In other words, you cannot have sound unless something is vibrating to create that sound. In terms of the answer for the second checkpoint question, a material medium is important to carry what we call mechanical vibration energy from the source to our ears. So in other words, we need to have some sort of medium in order to carry that energy which is produced, that sound energy, which really is the vibrational energy. We need a medium in order to allow the transmission of that vibrational energy from the source. And remember, that vibrational energy can only be transmitted if particles in the medium are allowed to vibrate. And then in terms of the third question, the answer to that question is that the three requirements of sound are, and they are the source of vibration, so we need to have a source which is undergoing some form of vibration. Then also we need to have the transmission medium in order to carry the sound vibration from the source to its destination. And then finally we need something to receive the sound vibration, and in this case it's our ears. So that would be the destination. Now, in terms of the answer to the fourth question, in terms of what is vibration, well, vibration is the disturbance or the to and fro motion of an object. And we've seen examples of the vibration in terms of what we've looked at so far in Unit 7.1 and 7.2. And question 5 actually gives us examples of those types of vibration. So, for example, a guitar string, a tuning fork, a drum, or a flute that you blow through, and the vocal cords in our vocal cord area of our neck, our throat. These are sources of sound. So hopefully these checkpoint questions have helped you to understand what we've looked at so far in section 7.2. And as I mentioned earlier, some of the concepts that we've looked at in 7.2, they're really just going over what we've looked at in Unit 7.1. So hopefully this has been useful, and we're now going to move on to Unit 7.3. Welcome to the Unit 7, on sound. In this part of the unit, we're going to focus on section 7.2, entitled Production and Transmission of Sound. Now, in this unit, we're going to focus on a number of learning objectives. And the learning objectives are as follows. In this subunit, students will be expected to be able to understand how sound is produced. And students will also understand how sound is transmitted. In addition, you will be expected to explain whether or not the speed of sound is constant for all materials. And in addition, you will also be expected to describe what elasticity and density are, and what is the relationship that elasticity and density have to the speed of sound. Now, some of these learning objectives relate to the content in terms of subsection 7.1 that we looked at earlier. And so there will be some concepts that will be looked at again, but we will look at them in a little bit more detail. So let's have a look at the production of sound. Now we've seen that, for example, sound is produced as a result of the vibration caused by an object. And that vibration causes vibration of particles in the air or in the solid or even liquid or gas surrounding that object. So let's have a look at an example of an object vibrating which produces sound. So a vibrating ruler produces sound. So if we look at the diagram at the bottom right hand side of the slide, you'll see that if you place a ruler on a table and if you flick the end of the ruler, then what will happen is that ruler will vibrate, and in so doing it will generate sound energy which you will hear. And also, if we take, for example, a long stretched rubber band, that rubber band, we can actually stretch it and flick it so that it produces sound. In other words, the vibrating rubber band will produce sound. And we've seen also in section 7.1 that vibrating musical instruments also produce sound. And also we've seen that the vibration of a tuning fork transfers its vibration to a vertically suspended pitch ball. And so we've seen that the air near a vibrating object is actually set in motion in all directions radially. So in other words, in this diagram here on the right hand side, we have in fact two illustrations of the vibration of a tuning fork and also the vibration due to a ruler. And these are examples of the production of sound. So there are other examples of production of sound that you're probably familiar with, especially in terms of musical instruments. So for example, what are the vibrating parts associated, for example, with the musical instruments such as a drum, a guitar, a chorale, a masinko, and a flute? So all of these instruments have some part of the instrument which vibrates, which generates sound waves that we can actually hear. Now, we can actually show that, for example, sound can be transmitted through a liquid. So if we had an alarm clock and we suspended that alarm clock in water, and we obviously make sure that the alarm clock is ringing before we suspend it in water, then once we've suspended it, you should still be able to hear the alarm ringing. In other words, sound is transmitted through a liquid. And this is an experiment that you could actually try in the lab. You could get, for example, a beaker and fill it with water, and then place in that beaker any device that generates a sound. And what you'll find is that you'll be able to hear the sound through the water. Now you can also show quite easily that sound is transmitted through solids. And this shouldn't be much of a surprise to you. So for example, if we were to get a loudspeaker and place it the other side of a wall, and we were to stand at the other side of the wall, then you would still be able to hear sound coming through that wall. In other words, you will be able to hear transmitted sound. Now obviously, once you have a source of sound waves, and those sound waves are, we can call it incident sound, once that's incident onto the wall, that means once those sound waves hit that wall, then you're going to get some of the sound waves which are reflected away from the wall. And we've seen this in section 7.1. But you will also get some transmitted sound. And in addition, you'll also get some sound that is absorbed. So this diagram really is a good diagram to show you what happens when sound waves are incident onto a wall. Some of the sound waves will be transmitted sound, some of the sound waves will be reflected sound, and some of those sound waves will be absorbed by the solid wall. Now, there are ways to show that sound can also be seen not to travel through a vacuum. In other words, if we were to place a bell, a ringing bell, and we connected up, for example, this bell or buzzer to a battery source and a switch, and we placed it in a bell jar, and we pumped out all the air from that bell jar, as the air is taken out of the bell jar, that the sound from the electric buzzer begins to diminish. It becomes less and less audible, and you will reach a point where you won't be able to hear the sound from the electric buzzer, despite the fact that you will see that the electric buzzer is ringing. So the buzzer is still ringing, but you can't hear any sound. And that is because sound cannot travel through a vacuum. Again, we've looked at this in section 7.1, and so this is really just recapping what we've already looked at in the previous subsection of the unit on sound. Well, as you've seen, sound does travel through various medium. And we've seen that sound can travel through a solid, sound can also travel through a liquid, and sound can travel through air. Let's have a look at a scenario. Let's have a look at a situation, an imaginary situation, but this is a good situation to demonstrate how fast sound can travel through various media. Let's imagine you are in a long mining tunnel deep under the earth, and you have a friend, and your friend is about 7,000 feet away from you in the tunnel. So you've got this very long tunnel, and you've got your friend at the other end of the tunnel, and your friend is standing about 7,000 feet away, which is quite a long distance. Now, let's imagine you and your friend can communicate by a phone, for example, or a walkie-talkie. And so you tell your friend, using the walkie-talkie, you tell them to yell, to shout, and at the same time that they shout, in fact, exactly the same time that they shout, they must hit on the pipes on the tunnel floor. So if you look in this diagram, you can see that there are some pipes running along the tunnel floor. If your friend is at the end of the tunnel and you tell them on the walkie-talkie to shout as loud as they can and hit the pipes at the same time, then what do you expect will happen? Now, in order to see what could possibly happen, let's have a look at the animation. So remember what you're doing. You're actually telling your friend to shout and at the same time to hit the metal pipes which are on the floor. So let's have a look and see what happens.
Hello. Hello.